candy bar can melt in the microwave without fire instead. Let me show you some video so you can understand.
Scientist Percy Spencer was performing experiments on a device called a magnetron. Magnetrons generate powerful microwave radiation. During the experiment, he observed that the candy bar in his pocket was completely melted.
Can you show me the application of the microwave? Let's continue watching this video.
From this experiment, it was observed that a high-powered traveling microwave has the capability of heating food. But of course, this raises the question of what was in the microwave that melted the candy bar. Microwaves are electromagnetic waves in a particular spectrum. Like any other electromagnetic waves, they have oscillating electric and magnetic fields. If you track amplitude of the wave in a specific area, you can observe this oscillation. In the chocolate melting accident case, the oscillating electric field component of the electromagnetic wave is responsible for cooking the food.
I still cannot understand, Mona. Let's see how oscillating electric field cook the food.
Most of the food that we consume has water in it. Water is a polar molecule. The hydrogen atoms of the water molecule are placed at an angle of 104 degrees from each other, and both the hydrogen and oxygen atoms have charges. This makes the water molecule behave like a dipole. When an electric field is applied to the water molecule, it starts to rotate due to the torque produced on the dipole. Since in electromagnetic waves the electric field oscillates continually, the water molecules will keep on oscillating. Due to this oscillating rotation, the molecules rub against each other and produce friction and heat in the food. Now, let's look at how to convert this heat generation concept into a workable product. To use the electromagnetic wave's energy efficiently, it must be reused several times. An efficient way of achieving this is to reflect it and keep it confined in a particular area. The best way of making this reflector is with the help of metal. The metallic surface causes the microwave to reflect from its surface, and if you keep one more reflector at the source side, the reflection will keep on continuing. This way, we will be able to trap the energy of electromagnetic radiation within a volume. However, the most efficient way of trapping electromagnetic wave energy is by use of a technique called resonance cavity. This method also increases the intensity of electromagnetic waves. Let's understand the concept of resonance cavity using a simplified approach of standing waves. A standing wave is a stationary wave that fluctuates in time but does not propagate in space. Just by observing these two wave animations, you can understand how a standing wave is different from a normal traveling wave. It is formed when two waves having the same amplitude and the same frequency, moving in opposite directions, are superimposed on each other. Please have a look at these two electromagnetic waves, which are traveling in the opposite direction. Let's pause the animation here. You can see that the waves have 180 phase differences here. When you add both the electromagnetic waves, they will perfectly cancel. Now let's pause at this instant. The resultant is a bigger sinusoidal curve. Let's pause at one more instance. Here you are getting an even bigger sinusoidal wave as the output. By comparing the results of these three instances, it is clear that the resultant electromagnetic wave just oscillates in its position without traveling. Let's examine how to produce two oppositely traveling waves practically. We will get a clear solution for this if we understand how electromagnetic waves get reflected on a metal surface. We know that when a wave meets a reflector, it returns to its source. Can you spot any connection between this reflected and incident wave? The reflected wave is, in fact, the wave that would have traveled forward if there were no reflector. First, of course, you have to fold this imaginary part 180 degrees, as shown. Now, let's add one more reflector, this time at the side of the source. This will reflect the same way again and produce a third wave, and this process will repeat. However, if you keep the second reflector at the intersection point of the first and second waves, the third wave produced after the reflection will be the same as the first wave. This is a clever arrangement. When you arrange the second reflector this way, we will see only two waves traveling in opposite directions, instead of many reflected waves and chaos. If you find out the resultant of them, it will be a standing wave. This is a well-known fact. The standing waves get produced when the distance between the source and reflector is an integer multiple of half wavelength. Thus, the dimensions of the closed structure are determined by the wavelength of these waves. Now, a fun fact. Just measure the cavity length of the microwave oven in your kitchen. It will be an integer multiple of this wavelength. It is clear from this visual that some points of the standing wave are at high energy intensity, and some other points are at zero intensity. Due to this, there would be many spots in a microwave, some cold and others hot.
Can you show me how to overcome the problem of the microwave?
Let's continue watching this video.
Nowadays, a microwave consists of a rotating plate, which helps the food cook evenly. The component responsible for producing microwaves is known as a magnetron. A magnetron emits microwaves in all directions. To confine the wave to propagate in one dimension, the magnetron is attached to the waveguide. From the waveguide, the waves come into the cooking chamber to heat food. Another question that has to be answered is whether microwaves are the only electromagnetic waves capable of heating food, or if there are any other waves that could accomplish the same result. Any electromagnetic waves have the capability to heat food, but they come with certain limitations. Waves with long wavelengths can easily pass through our food so that they won't be able to transfer much energy to it. Additionally, to get standing wave, large devices will be required. Shorter wavelength waves are absorbed more rapidly on the outer surface of the food, so they do not penetrate far enough down to cook it evenly. If we want to cook deeply, we have to switch to a very high power source that would be unfeasible. In the microwave range, the suitable frequency for all practical purposes and which did not require a license was 2.45 GHz.
There are three major components of microwave oven. First, magnesium waveguide. Microwave stirrer. One magnetron is the core of microwave. This component is responsible for converting electrical energy into microwave radiations. To our guide is component designed to direct microwave. Microwave waveguide is made from conductor and material. Three microwave stirrer. This propeller shaped component functions to spread microwave in the microwave. How it works? When cooking microwave, magnetron current to produce microwave. Then the microwave will be directed by the antenna at the top of the magnetron into the waveguide and transmit microwave to a fan-like device called the stirrer. Then the stirrer spread microwave in the oven chamber. This microwave are then reflected by the wall in the oven and absorbed by food molecule.
Microwave can interact with compounds that have dipole moments, such as water, because heat relay has an electrical field, and the magnetic field compound or positive-negative feed molecules are pushed back and forth 2 times the speed of the microwave frequency, which are about 0.9 billion of times per second. Therefore, they will rotate as they try to align themselves with changing electric field induced by microwave.